Greetings and welcome to Dr. Lisa's Quick and Dirty Guide to the T-Test, Part 3, Repeated Measures. Now, the first video in this series is basically laying groundwork. The second was the most basic kind of T-test, which is comparing a sample mean to a population mean. And so what we're going to do here now is we're basically going to compare two sample means to each other. This is a lot more like what you would be doing in your experiments. You'll have a experimental group and a control group, and you're going to compare the means to each other. And so what we're going to do in this chapter is we're going to do what's called repeated measures or dependent measures or, related measures. There's all sorts of names. But what we're talking about here is that these cases were not selected independently of one another. In other words, they're related. So what happens sometimes, which we'll learn more about later in the class, is that you might, for instance, want to do a single subject designs, or what might be called a repeated measure design, or within subjects design. Okay, where for instance you have a group of people, you measure the dependent variable, you give them whatever medication that you hope to be treating them with. And then after you've treated them, you measure the dependent variable again. And then very often what you might do is take them off the medication to see what happens when they go off, what happens to the dependent variable then. And then you might put them back on the medication, which is sometimes called an AB-AB design. So it's the same subjects in both groups. That's within subjects research. Sometimes you may also use what's called a matched group. You may want to make sure that your groups are matched on some sort of variable, that they're all exactly the same age, or that, if you've got older people, you have the same number of older people in both groups and the same number of younger people, there's various ways to match. We'll talk about it later. And it could also be if you're dealing with people who know one another. So it's in some ways it's not truly random assignment because it's the same people in both groups in some way, so they're related somehow. But the idea here again is that you're basically comparing these two groups, let's call them the experimental and the control group, just for fun, to each other. So we're looking at how extreme the difference is as compared to all possible differences. And with that, as before, we're going to use numbers and various formulas. Although, as I mentioned, they're going to look pretty similar. Yeah, since this is not a population, then since these are samples, we need to take into account that there's all kinds of samples, all sorts of variation that could take place. So, t-test for the difference between means, related or dependent samples. The first thing you do is you take those pairs, whatever those pairs are, whether it's before and after, whether it's people in this group that's matched with the person in this group, or this spouse with their spouse in the other group. So however they're matched, you try to find the difference between the two. And that's called X sub D. That's the difference between those two scores. The score of the person in the first group and the match score in the second group. Now, one of the test statistics is the mean of these differences, and we're going to call that, XD bar. Unfortunately, that's left over from before. It's actually X sub D bar. Boy, it's a good thing you don't have to say these often very much. Which is essentially the sum of all of the differences of each pair's difference. You sum them all up and you divide them by n. It's an average, but it's an average of the differences. Okay? It's not an average of the scores. It's the averages of the differences between the scores. That's what the D is for. So, yeah, you've got all these pairs. If you have 11 pairs, you'll wind up with 11 differences, because each of those is the difference between the first and the second. And then how do you find X sub D bar, or X bar sub D, or whatever the hell you say that? How do you do that? You basically take those 11 scores, you add them up, and you divide them by 11. And you find an average, you find a mean. With that, we could find the standard deviation of the differences. using your general standard deviation. This is how you find a standard deviation. Again, this is a lot scarier than it looks, because underneath that particular square root, what it is, it's the sum of xd minus the mean of all of the differences. I'll say it that way. So you take your one score, score number one, the difference between the first pair. You subtract the mean of all the scores from it, and then you square that difference. And then you take the second one, and you take the difference, and you subtract the mean of the differences, and you square that. And then you take the third one, you take the difference, you subtract the mean of the differences, and then you square that, and then you add up all those squared numbers together. That's what that big sigma is for. That's for sum. You divide it by n minus 1, the degrees of freedom. So you divide it by 10 in this case, since there's 11 scores. And then you take the square root of it. Bingo! Standard deviation. Break these formulas down. Don't look at them as a whole. They'll freak you out. Break them down. You know what x sub d is. You know what the x bar sub d is. You know what squared is. You know what that big sigma is now. You know what n is. Just plug the numbers in. Now this also can be known as the square root of what's called the sum of squares. That number on the top is known as the sum of squares. This is one of those things that you kind of missed if you haven't taken descriptive stats, but it's the sum of squares divided by the degrees of freedom. You're probably going to more likely use the first formula, but I would recognize both of them. Once you have that, well, that's when you start sitting down and saying, okay, let's phrase this. The null hypothesis is that there's no difference between the groups. That the mean of the first group is the same as the mean of the second group. That's the null hypothesis, because remember, the null is always there's no difference. And this is a little explanation that you can either understand or you could take it on credit, because basically there is no difference between the groups. That's what we're assuming, because that's the null. It means that the mean of the sampling distribution of mean differences is also 0. So remember that fun little mu that we were using like in the t-test? That's going to be 0. So we need to know the standard error of the mean difference. We'll get back to that in a second. And the standard error of the mean difference looks just like the standard error of the mean scores that we had before. So we have S sub x bar sub d is equivalent to S sub d, which we've figured out, divided by the square root of n. It's the same formula from the last chapter. It's just got different numbers in it. Okay? So here we go. That should look very familiar. It's the same as the t in the prior one. It's the same as the z. It's just got slightly different numbers. So we have x bar sub d minus basically the population means. The difference between the population means, which we figure we know something about, the same we did before, divided by the standard deviation of x bar sub d, which we just found out on the prior screen. And like I said, it sounds a lot more complicated than it is. And the nice thing is, remember I was telling you that we're assuming that the difference between the means is 0 because there's no difference? We can ignore that. This is the actual equation that you're using. X bar sub d divided by s sub x bar sub d. So the mean of the differences divided by the standard deviation of the differences. That's it. Granted, there's a lot more work than that. If you're not given, for instance, the sum of squares or the standard deviation, you're going to have to sit and figure all those out. Okay? But, you know, and then you're also going to need to figure out basically the mean of the differences. But I just told you how to do that in those prior two screens. And then lastly, just like before, we look up that t-score, we compare it to our critical value, and then we determine whether or not it's more extreme than the critical value, and if it is, then we say that it is significant. Here's a step-by-step. I like to do a step-by-step when things get complicated, so you're going to see more of this as we go on. So identify the null and identify the alternative. Now, you're not always going to need to do this, but it's never a bad idea to do it. because it'll help you think about it a little more clearly. Find the level of significance. This will be in the question. Okay? I will tell you if it's 0.05 or 0.01. Okay? I will tell you, well, actually from your hypothesis, you'll know whether it's one-tailed or two-tailed. If it's equal or not equal, then it's two-tailed. You're going to use both extremes. If it's equal and larger than, or if it's equal or smaller than, it's one-tailed. And you're going to do a slightly different. Okay? That's why it helps to state the hypotheses. So you can actually look at that and go, oh, it's one-tailed, or oh, it's two-tailed. It will say so in the question. Not that it's one or two-tailed, but what the differences are. Once you've got the level of significance, write that down. Plus or minus, whatever it is. Identify the degrees of freedom. Again, that's the number you have, -1. Determine the critical value. Look that sucker up. Degrees of freedom on one axis. And your alpha level, your significance level on the other, probably 0.05 or 0.01. Find where they intersect. That's your critical value. Calculate D and S sub D. Once you get the differences, that should be X bar sub D again. I apologize. And S sub X sub D. Ignore the stuff on the left. Look at the right. Those are your formulas, okay? Sorry, I adapted this from a prior class, and it turns out that every damn statistics text uses their own abbreviation. Calculate the standardized test statistics compared to critical value. Again, focus on the stuff on the right there. Make a decision to reject or fail to reject. Once you compare your t-value, if the t-value is more extreme than the critical, then you're going to reject the null. Otherwise, you're going to fail to reject the null. And then interpret it. Say, well, it looks like there isn't a difference, or it looks like there is a difference with this significance. It's plugging numbers into a formula, and once you know what the numbers are, and you're not frightened off by S sub X bar D, it's not nearly as bad as it might seem. Okay? An example. Examples are always good. Assuming two matched samples, each involving 10 cases, therefore n equals 10. There's one of your numbers, and the following information. The mean of the differences. See, this one's giving you the numbers. All you got to do is plug them in and do the math. By the way, you are allowed to use a calculator for this. Okay? You are allowed to use a calculator. Please don't use a programmable one. I don't want you programming the stuff in pre-hand. I prefer you use a nice cheap-ass one you got from the dollar store or something. Okay? Don't use a programmable calculator. So the mean of the differences, X bar sub D is 11.65. The estimated standard error of the mean differences, S sub X bar D is 3.39. Calculate T, assuming a 0.05 level of significance. Do you reject or fail to reject? This is probably going to look quite a bit like a question you're going to get. I mean, there may be one or two that require you to actually find the sum of squares and whatnot, but this should be pretty close to what you're going to get on the test. And now that you have all these numbers, all you frankly have to do is plug them in. Whoop, sorry about that. Since this is equal to this, you plug the numbers in, and there's your t. I mean, it's this divided by that. Get your t-score. Fantastic. What's your degrees of freedom? 10 minus 1 is 9. There's your alpha level, which happened to pop in before everything else. So it's plus or minus 2.2622. Fantastic. You're at 3.4. It's more extreme. So we reject the null at the 0.05 level of significance. Like I said, I'm trying not to make this complicated because it's mostly a research methods course. When you take a statistics course, we'll go into all the whys and wherefores and hows and whatnot. And you're welcome to learn that on your own. But mostly here, I just want you to be familiar enough with this that you could do this statistic if I gave it to you. And actually by doing it step by step, as opposed to plugging it into SPSS, it actually might help you understand where these numbers are coming from. And that's the end of Chapter 9.